The asteroid that killed the dinosaurs didn't kill them all at once. That's the part of the story nobody tells you. When the 6-mile-wide rock slammed into the Yucatán Peninsula with the force of 10 billion atomic bombs, it didn't flip a switch and turn off every dinosaur on Earth. The impact was catastrophic. Yes, it vaporized rock, ignited forests across continents, and threw so much debris into the atmosphere that the sky went dark for months. But in the immediate aftermath, in the hours and days and weeks that followed, some dinosaurs were still alive. They were walking through ash-covered forests, drinking from poisoned rivers, and trying to survive in a world that had just been shattered. The extinction wasn't instant. It was slow, brutal, and drawn out across thousands of years. This is the story of what really happened after the asteroid hit, the prolonged dying of the Mesozoic world. The first minutes, shockwave and inferno. The asteroid struck at approximately 20 kilometers per second, punching through the atmosphere like it wasn't even there. The impact site, now known as the Chicxulub crater, exploded with energy, equivalent to 100 trillion tons of TNT. The bedrock vaporized instantly, and a plume of superheated rock and gas shot upward into the stratosphere. Within seconds, the shockwave radiated outward at speeds faster than sound, flattening forests and killing everything within hundreds of kilometers. Dinosaurs standing near the impact site didn't have time to react. They were incinerated before their nervous systems could register what was happening. The ground buckled and heaved as seismic energy rippled through the Earth's crust, triggering earthquakes that registered magnitude 11 or higher on the Richter scale. Trees older than centuries toppled like matchsticks. Mountains shifted. Coastlines crumbled into the sea. But farther from the crater, in what is now North America, Asia, and South America, dinosaurs felt the ground shake beneath them. Seismic waves rolled across continents like invisible tsunamis, toppling trees and triggering landslides thousands of kilometers from the impact zone. Herds of triceratops grazing in floodplains would have stumbled as the earth buckled beneath their massive feet, their three-horned heads swinging in confusion. Tyrannosaurs hunting in forests would have roared in confusion as the world convulsed, their keen predatory instincts suddenly useless against a threat they couldn't see or fight. The shaking lasted for minutes that felt like hours, then subsided into an eerie, unnatural stillness. For a brief moment, the survivors might have thought it was over. They might have gone back to grazing, to hunting, to the rhythms of life that had governed their existence for millions of years. Then the sky began to glow. The debris ejected by the impact, trillions of tons of vaporized rock, had been launched into space, climbing through the atmosphere on columns of superheated gas. Now it was falling back down. As it re-entered the atmosphere, friction heated the particles to temperatures exceeding 1,000 degrees Celsius. The entire sky turned red, then orange, then white-hot, as if the heavens themselves had caught fire. This thermal pulse radiated across the planet, cooking everything exposed beneath it. Forests ignited spontaneously, bursting into flame without warning. Animals caught in the open were roasted alive, their bodies charring as temperatures spiked to levels comparable to industrial furnaces. Dinosaurs that had survived the initial shockwave now scrambled desperately for cover, diving into rivers, retreating into caves, burying themselves in mud, pressing their bodies against the cool earth in a futile attempt to escape the heat. Those that found shelter had a chance. Those that didn't were reduced to ash within minutes. The infrared radiation lasted for hours, transforming the planet's surface into a furnace. Recent computational models suggest that temperatures spiked high enough to cause spontaneous combustion of organic material across entire continents, with surface temperatures reaching 400 degrees Celsius in some regions. The air itself became unbreathable, thick with smoke and superheated gases that seared lungs and throats. Small dinosaurs, with their higher surface area-to-volume ratios, would have overheated faster, their bodies unable to shed heat quickly enough. Larger species like sauropods and hadrosaurs could retain body heat longer, but that became a liability in this scenario. They couldn't cool down fast enough, and their massive bodies became ovens that cooked them from within. Paleontologists have found charcoal layers in the geologic record corresponding to this event, evidence of wildfires that burned simultaneously across North America, Europe and Asia, consuming forests that had stood for millions of years. Beneath the chaos, some pockets of life endured. Dinosaurs submerged in deep water, where thermal inertia protected them from the worst of the heat, had marginally better odds. Those burrowed underground, insulated by meters of soil and rock, survived the thermal pulse. Some sheltered in dense vegetation or beneath rocky overhangs, places where shadows and moisture created micro-refuges. But even they faced a new problem. The air was filled with toxic particles. Sulfur dioxide, nitrogen oxides and pulverized rock formed a choking haze that spread globally within days, carried by high-altitude winds that circled the planet. Breathing became difficult. Vision became limited. The world that had been bright and vibrant just hours earlier was now dim, suffocating and hostile. The survivors emerged into twilight, coughing and disoriented, to find their world transformed beyond recognition. The first days, darkness falls. When the thermal pulse finally faded and the fires burned themselves out, the survivors emerged into a world transformed beyond recognition. The sky, once a brilliant blue that stretched from horizon to horizon, was now a sickly grey-brown, choked with dust and aerosols suspended in the atmosphere. Sunlight barely penetrated the thick blanket of particles, casting everything in a perpetual twilight that felt unnatural and oppressive. This was the beginning of what scientists call impact winter, a prolonged period of darkness and cold that would last for months, possibly years, fundamentally altering every ecosystem on Earth. Photosynthesis ground to a halt. Plants that had survived the fires now began to wither and die without sunlight, their leaves turning brown and dropping to the ash-covered ground. For herbivorous dinosaurs, this was the start of a slow-motion catastrophe. Hadrosaurs, like Edmontosaurus, which relied on vast quantities of vegetation to fuel their massive bodies, consuming hundreds of kilograms per day, found themselves in a dying landscape. The ferns and conifers they browsed were turning brown and brittle. New growth had stopped completely, the plants entering dormancy or simply dying as their energy reserves ran out. Within days, food became scarce. Herds that once roamed freely across wide territories now competed desperately for the few remaining patches of edible plants, their social structures breaking down under the pressure of starvation. Weaker individuals began to die first, the very old, the very young, those already injured or sick. Calves and juveniles with higher metabolic demands relative to their body size succumbed within the first week, their bodies too small to carry sufficient fat reserves. The carnivores faced a different but equally dire problem. Tyrannosaurs and smaller theropods like Dromaeosaurus didn't eat plants, so they weren't immediately affected by the collapse of photosynthesis. But their prey was dying. Herbivore populations began to crash as starvation set in, and the predators followed in a cascade of extinction that rippled up the food chain. A Tyrannosaurus needs enormous amounts of meat to survive. Estimates based on metabolic models and body size suggest an adult required several hundred kilograms per week, roughly equivalent to one full-grown hadrosaur every 7 to 10 days. With prey becoming scarce, these apex predators had to scavenge more and hunt less, a dramatic shift in behavior for animals built to kill. Fossil evidence from this period shows bite marks on bones consistent with scavenging behavior, deep tooth scores that indicate tyrannosaurs were stripping every scrap of meat from carcasses, even cracking bones to access the marrow inside, something they rarely did when prey was abundant. The temperature dropped rapidly as the dust and aerosols reflected sunlight back into space. Without solar radiation to warm the surface, the planet cooled. Within weeks, global temperatures may have plummeted by as much as 20 degrees Celsius, transforming tropical paradises into cold, barren wastelands. Dinosaurs, which many paleontologists now believe were mesothermic, maintaining body temperatures somewhere between cold-blooded reptiles and warm-blooded mammals, struggled to adapt to the sudden cold. Species living in polar regions or high altitudes already accustomed to cooler climates and seasonal temperature variations, fared slightly better. But tropical species, which had evolved in stable, warm environments for millions of years, had no physiological mechanisms to cope with the cold. Their bodies, optimized for heat dissipation, now worked against them as temperatures plummeted. Water sources became contaminated. Ash and debris settled into rivers, lakes, and coastal zones, turning them acidic and toxic. The pH of freshwater systems dropped dramatically as sulfuric acid rain fell from the polluted skies. Fish populations collapsed, depriving pterosaurs and semi-aquatic dinosaurs of a critical food source. Fossil sites from the Hell Creek Formation show a sudden disappearance of freshwater fish species at the boundary layer, evidence of catastrophic ecosystem collapse. Spinosaurids and other fish-eating dinosaurs, already rare by the end of the Cretaceous, would have faced immediate starvation as their specialized diet became unavailable. The psychological toll on these animals is harder to measure, but no less real. Dinosaurs were intelligent creatures, with complex social structures and learned behaviors passed down through generations. The sudden collapse of their world would have caused confusion, panic, and disorientation. Herds that migrated seasonally along established routes found their paths blocked by impassable terrain. Forests reduced to charred stumps, rivers choked with debris, familiar landmarks obliterated. Nesting sites were buried under meters of ash, destroying eggs and forcing parents to abandon reproductive efforts. Communication calls that once carried across open plains were muffled by the dense, particle-filled atmosphere. The survivors were navigating a nightmare, their instincts and learned behaviors suddenly useless in a world that no longer made sense. The first weeks, ecosystem collapse. By the end of the first month, the true scale of the disaster became clear. The food chain, which had sustained Mesozoic ecosystems for more than 160 million years, was disintegrating from the bottom up. Plant life, the foundation of every terrestrial ecosystem, was dying en masse. Without photosynthesis, primary productivity dropped to near zero. The few plants that survived did so by drawing on stored energy reserves in roots and tubers or by entering dormancy, strategies that helped them weather the crisis but didn't provide food for herbivores. The landscape was transformed into a grey wasteland of dead vegetation, ash-covered ground, and skeletal trees that stood like monuments to a vanished world. Insects, which had co-evolved with dinosaurs and flowering plants throughout the Cretaceous, were hit hard. Many species that depended on nectar, fresh leaves, or fruit went extinct within weeks. The delicate symbiotic relationships between plants and their pollinators, relationships that had taken millions of years to evolve, were severed in an instant. Pollinators disappeared, further accelerating the collapse of plant communities and creating a feedback loop of extinction. The fossil record shows a dramatic reduction in insect diversity at the Cretaceous-Paleogene boundary, with some groups losing more than 70% of their species. For small insectivorous dinosaurs like Troodon, which relied on insects as a primary food source and had evolved specialized hunting techniques to catch them, this was catastrophic. These intelligent, bird-like predators found themselves in a world suddenly devoid of prey, their keen eyesight and quick reflexes useless. Larger herbivores began to succumb in greater numbers. Ceratopsians like Triceratops, which had thrived in the late Cretaceous and dominated many ecosystems, found themselves stranded in barren wastelands. Their massive frills and horns, once used for defense against tyrannosaurs and for elaborate courtship displays, offered no protection against starvation. These 3-ton animals required enormous amounts of food daily, and as the vegetation disappeared, they weakened rapidly. Fossil bone beds from this period show mass mortality events, dozens of individuals dying in close proximity, likely as herds gathered around the last remaining water sources and succumbed together, their bodies piling up in grim testimony to the scale of the catastrophe. Theropods turned on each other as desperation mounted. With prey populations crashing, cannibalism became more common. Bite marks on Tyrannosaurus bones from this era show evidence of intraspecific violence. adult tyrannosaurs attacking and feeding on members of their own species, something that appears to have been rare during normal times. This wasn't typical behaviour for these animals, which seem to have maintained complex social structures and possibly even hunted cooperatively. But desperation drove them to it, breaking down social bonds and turning former packmates into food sources. Some smaller theropods may have shifted to scavenging exclusively, feeding on the growing number of carcasses littering the landscape, developing new behavioural patterns in a desperate bid for survival. Aquatic ecosystems fared no better. The asteroid impact had triggered massive tsunamis hundreds of metres high that scoured coastlines and reshaped shallow seas. The debris fallout acidified ocean waters, causing widespread die-offs of plankton and marine invertebrates. Ammonites, shelled cephalopods that had survived multiple extinction events over hundreds of millions of years and had weathered the end-Triassic and end-Jurassic mass extinctions, were wiped out. Mosasaurs, the dominant marine reptiles of the late Cretaceous, some species reaching lengths of 15 metres, lost their primary food sources as fish populations crashed. Fossil evidence suggests they survived for weeks or even months after the impact, but eventually starvation claimed them too. These apex predators reduced to scavenging dead fish and marine carrion before succumbing. The skies were no safer. Pterosaurs, the flying reptiles that had ruled the air for 160 million years and had diversified into dozens of ecological niches, faced a dual crisis. The collapse of fish populations eliminated the primary food source for many species, while the darkened skies and turbulent atmospheric conditions made flight dangerous and energetically expensive. Large pterosaurs like Quetzalcoatlus, with wingspans exceeding 10 metres and standing as tall as giraffes when on the ground, required enormous amounts of energy to stay aloft. Without reliable food, they couldn't sustain flight or even basic metabolism. Grounded and starving, these giants became easy prey for opportunistic scavengers, their massive bodies providing temporary windfalls of food for desperate predators. The first months, the long starvation. 3 months after the impact, the world was unrecognisable. The sun remained hidden behind a thick veil of aerosols, casting the planet into perpetual twilight. Temperatures continued to drop, and in some regions, snow fell for the first time in millions of years. White flakes drifting down onto landscapes that had known nothing but tropical warmth since the Triassic. Dinosaur populations, already decimated by the initial fires and the subsequent starvation, continued to decline. The survivors were skeletal, malnourished shadows of their former selves, their ribs visible through thinning skin, their movements slow and laboured. Herbivores were reduced to eating bark, dead wood and fungi, anything that might provide calories. Some species developed behavioural adaptations on the fly, learning to dig for roots with their beaks or strip bark from trees with their teeth. Behaviours never seen in their ancestors. But these strategies were stopgaps, not solutions. The energy expenditure required to find food often exceeded the calories obtained, creating a downward spiral of weakness and desperation. Starvation was inevitable. Fossil evidence from the Hell Creek Formation shows bone pathologies consistent with severe malnutrition, thinning cortical bone, lesions from vitamin deficiencies, and stunted growth in juveniles. Some specimens show evidence of metabolic bone disease, a condition caused by inadequate calcium intake, resulting in deformed and fragile skeletons. Predators fared little better. With herbivore populations collapsing, carnivores had no sustainable prey base. Tyrannosaurus, once the apex predator of North America and one of the most successful large predators ever to evolve, was reduced to scavenging and opportunistic hunting of whatever small animals remained. Some individuals may have turned to fishing in desperation, wading into rivers to catch whatever remained of the dwindling fish populations. But fish were also dying off rapidly, poisoned by acidified water and starved of their own food sources. The effort required to catch them often wasn't worth the minimal reward. The last tyrannosaurs likely died alone, weakened by hunger and unable to maintain their territories, their powerful jaws and massive bodies ultimately useless against an enemy they couldn't fight. The few pockets of relative stability were found in environments buffered from the worst effects of the impact. River valleys with dense vegetation cover, where topography had protected some plants from the thermal pulse, offered temporary refuges. Coastal marshes fed by nutrient-rich runoff from eroding highlands provided slightly more food than the barren uplands. Volcanic regions with geothermal heat created microclimates where temperatures remained marginally higher, allowing some plant growth to continue. Some dinosaur species clung to life in these isolated havens, but they were evolutionary dead ends, cut off from larger populations and unable to migrate as barriers of ash and devastation separated them from other survivors. They faced genetic bottlenecks and inbreeding. Even if they survived the immediate crisis, they lacked the genetic diversity necessary to rebuild viable populations. Smaller animals had a distinct advantage. Mammals, which had spent the entire Mesozoic era in the shadows of dinosaurs, kept small and nocturnal by the dominance of their reptilian contemporaries, were better equipped to survive. Many were burrowers, which protected them from the thermal pulse and insulated them from the cold. They had lower metabolic demands than dinosaurs of equivalent body mass, requiring less food to survive on a daily basis. And they were omnivorous, able to eat seeds, insects, carrion, and even detritus, resources that remained available even as larger ecosystems collapsed. While dinosaurs starved, mammals endured, their small size and behavioral flexibility proving to be unexpected advantages in the post-impact world. Birds, the descendants of theropod dinosaurs and the only dinosaur lineage that would ultimately survive, also persisted in significant numbers. Small-bodied, warm-blooded, and capable of flight, they could exploit niches unavailable to their larger relatives. Seed-eating birds, in particular, thrived. Seeds are durable, capable of surviving months or even years in dormancy, resistant to heat, cold, and moisture. As plants died, they released seeds into the environment, creating a temporary food source that carried seed-eating birds through the worst of the crisis. This dietary flexibility, combined with their ability to migrate rapidly in search of better conditions and their capacity to adapt quickly to changing circumstances, allowed birds to survive where non-avian dinosaurs could not. The first year, a world of ash and silence. 1 year after the impact, the planet was a graveyard. The skies had cleared somewhat. Enough sunlight now penetrated the atmosphere to cast faint shadows and allow a trickle of photosynthesis to resume. But the damage was done. Entire ecosystems had collapsed completely. Forests that once teemed with life, filled with the calls of dinosaurs and the buzz of insects, were reduced to fields of charred stumps standing in ash. Riverbeds that had flowed with clear water were choked with sediment and ash, their channels altered by landslides and erosion. The silence was oppressive, broken only by the wind moving through dead trees. No birdsong, no insect hum, no distant calls of dinosaurs echoing across the plains. The world felt empty, abandoned, as if life itself had given up. The few dinosaurs that remained were ghosts haunting the ruins of their world. Small theropods, possibly including species related to modern birds, still prowled the devastated landscapes. They were thin, desperate, and solitary, their bodies gaunt from months of inadequate nutrition. Social structures had broken down completely. Herds had scattered, their members either dead or wandering alone in search of food. Nesting sites lay abandoned, eggs buried under ash or simply left to freeze in the cold. The rituals of courtship and reproduction, which had governed dinosaur life for millions of years and had been passed down through countless generations, had ceased. There was no future to plan for, only survival day to day, hour to hour. Plant life began a slow, tentative recovery. Ferns, which reproduce via spores and can tolerate harsh conditions better than seed plants, were among the first to return. The fossil record shows a fern spike at the KPG boundary, a sudden explosion of fern spores indicating rapid colonization of barren landscapes. This fern-dominated ecosystem has been observed at extinction boundaries worldwide from North America to New Zealand, suggesting it was a global phenomenon. But ferns alone couldn't rebuild a functioning ecosystem. They lacked the structural complexity and nutritional value needed to support large herbivores. The dinosaurs that had survived on whatever ferns they could find would have discovered them to be poor substitutes for the diverse plant communities they once relied on, lacking essential nutrients and calories. Flowering plants, which had revolutionized Mesozoic ecosystems when they first appeared in the Cretaceous and had formed complex relationships with dinosaurs and insects, struggled to recover. Many species had gone extinct during the impact winter, their seeds unable to germinate without adequate warmth and light. Those that remained faced a world without pollinators. The intricate networks of bees, butterflies, and other insects that had facilitated their reproduction now largely destroyed. The co-evolutionary relationships between plants and insects, fine-tuned over millions of years, had been severed in a matter of months. Some plants adapted by shifting to wind pollination or self-pollination, but these were slow, inefficient processes that resulted in reduced genetic diversity. The lush, flower-filled landscapes of the late Cretaceous were gone, replaced by sparse, primitive vegetation that would take millions of years to rebuild. The oceans remained in crisis. Acidification had killed off much of the plankton, the microscopic organisms that form the base of the marine food web and produce more than half of Earth's oxygen. Without plankton, fish populations couldn't recover, and without fish, marine reptiles and seabirds starved in a cascading collapse that emptied the seas. The recovery of ocean ecosystems would take hundreds of thousands of years, driven by the gradual weathering of rocks on land and the slow return of nutrients to the seas through river runoff. It wasn't until the Paleocene, millions of years later, that ocean productivity returned to pre-impact levels. For the mosasaurs and plesiosaurs that had survived the initial impact, this timescale was meaningless. They died within the first year, their massive bodies requiring food intake that the depleted ocean simply couldn't provide. On land, scavengers thrived briefly in a macabre boom. Carrion was abundant. Dinosaur carcasses littered the landscape, preserved by the cold temperatures and the lack of decomposers, which had also suffered massive die-offs. Mammals, small theropods, and opportunistic pterosaurs fed on the dead, growing fat on the remnants of the Mesozoic world, their populations temporarily swelling as food became paradoxically abundant. But this bonanza was temporary and unsustainable. As the carcasses rotted away or were consumed, the scavengers faced the same fate as the herbivores before them. Without a sustainable food source and without the ecosystems to support them, their populations crashed just as dramatically as they had risen. The first century, the final holdouts. 100 years after the impact, the question isn't whether dinosaurs survived in large numbers, it's whether any non-avian dinosaurs remained at all. By this point, the ecosystems that had supported them for 160 million years had fundamentally changed in ways that made their continued existence increasingly unlikely. The forests were different, dominated by new plant species that had evolved or migrated from refugia. The rivers flowed through altered landscapes, their courses changed by erosion and geological upheaval. The climate, while more stable than in the immediate aftermath, bore little resemblance to the hothouse world of the late Cretaceous, with its warm polar regions and lack of ice caps. If any dinosaurs persisted this long, they would have been living fossils in the truest sense, relics of a vanished age clinging to existence in isolated pockets cut off from the wider world. Think of them as the dinosaurian equivalent of the coelacanth, that ancient fish discovered in modern times, species that survived long past their apparent extinction by retreating to marginal habitats, where competition was low and conditions stable. Remote islands, deep valleys isolated by mountain ranges or isolated volcanic regions could have harbored small populations for decades or even centuries, protected from the worst of the climate chaos by their geography. The fossil evidence for such long-term survival is weak but not entirely absent, continuing to fuel speculation and research. Paleontologists have reported finding dinosaur fossils in Paleocene sediments in several locations, though these findings are often disputed and controversial. The most famous case involves hadrosaur bones discovered in New Mexico in rock layers dated to the Paleocene, roughly 64 million years ago, 700,000 years after the asteroid impact. If accurate, and if these bones are genuinely in their original position, rather than reworked, this would prove that at least some dinosaurs survived well into the Cenozoic era. However, critics argue vigorously that these bones were likely eroded from older Cretaceous sediments and redeposited by rivers or other geological processes, a common occurrence that can make dating difficult and misleading. Another possibility is that we simply haven't found the fossils yet. The fossil record is notoriously incomplete, preserving only a tiny fraction of the organisms that once lived. Some estimates suggest less than 1% of all species that ever existed have left fossils. Dinosaurs surviving in small, isolated populations would have left few fossils, and those that exist might remain undiscovered, buried in remote locations, or misidentified in museum collections. Until we have more data and better dating techniques, the question remains tantalizingly open, one of paleontology's great unsolved mysteries. What we do know with certainty is that by the end of the 1st century, the world had moved on. Mammals had radiated into dozens of new forms, filling ecological niches from tiny insectivores to dog-sized predators. Flowering plants had recovered and diversified, creating new ecosystems fundamentally different from those of the Mesozoic. The oceans, though still depleted compared to Cretaceous levels, were slowly rebuilding their food webs through the gradual return of plankton populations. The Mesozoic was over, its characteristic fauna and flora replaced by new forms. If any dinosaurs remained, they were shadows in a world that no longer belonged to them, the last representatives of a dynasty that had ruled for 160 million years. The role of secondary extinctions. One of the most overlooked aspects of the KPG extinction is the role of secondary extinctions, species that didn't die directly from the impact itself, but succumbed to cascading ecological failures in the months and years that followed. For dinosaurs, the collapse of plant communities was the primary trigger, but other factors compounded their decline in a complex web of interacting catastrophes. Understanding these secondary effects is crucial to understanding why the extinction was so severe and why recovery took so long. Parasites and diseases, which had co-evolved with dinosaurs for millions of years in intricate relationships, lost their hosts. Without dinosaurs to infect, many of these organisms went extinct themselves, though we have little direct fossil evidence of them due to their soft-bodied nature. But in the chaotic years following the impact, opportunistic pathogens may have spread more easily through stressed populations. Weakened, malnourished dinosaurs living in close proximity around dwindling resources would have been vulnerable to infections that healthy individuals in normal times could have fought off easily. Fossil evidence of disease in late Cretaceous dinosaurs includes bone lesions consistent with osteomyelitis, tumours that suggest cancer, and signs of parasitic infections, conditions that would have been exacerbated by post-impact stress and poor nutrition. Water scarcity was another compounding factor that intensified over time. The impact of winter disrupted the hydrological cycle, reducing precipitation in many regions as the atmosphere's temperature gradients weakened. Rivers dried up or became seasonal rather than perennial. Lakes evaporated under the dim sun, their water lost to the air faster than it could be replenished. Groundwater became inaccessible as water tables dropped. Dinosaurs, particularly large species with high water demands, a large hadrosaur might need hundreds of litres per day, would have struggled to find drinking water. Dehydration, combined with starvation and disease, created a perfect storm of mortality that affected even those individuals that had survived the initial catastrophe. Competition with other survivors also played a significant role in determining which lineages persisted. Mammals, though small, were highly adaptable and reproduced quickly, with generation times measured in months rather than years or decades. They competed with small dinosaurs for the same food sources: seeds, insects, carrion, plant matter. In this competition, mammals had the advantage of shorter generation times, allowing them to evolve and adapt more rapidly to changing conditions. Over time, they outcompeted the dinosaurs for the few remaining resources, occupying niches that small dinosaurs might otherwise have filled in the recovery period. Finally, there's the critical issue of reproductive failure. Dinosaurs, like modern reptiles and birds, laid eggs that required specific temperature ranges and environmental conditions to develop properly. The environmental chaos following the impact would have disrupted nesting behaviours in profound ways. Ash-covered ground provided poor substrate for nests, retaining too much or too little heat. Contaminated water sources near traditional nesting sites may have introduced toxins into developing eggs. Temperature extremes, both the cold of impact winter and the heat from volcanic eruptions, would have reduced hatching success dramatically, with embryos dying before they could develop fully. Even if adult dinosaurs survived in reasonable numbers, if they couldn't successfully reproduce and raise offspring to maturity, their populations would eventually die out regardless. This reproductive bottleneck may have been the final blow for many species, ensuring extinction even when individuals survived. Regional variations in survival. The extinction didn't unfold uniformly across the planet, creating a complex patchwork of survival and death. Different regions experienced different levels of devastation, depending on their distance from the impact site, their geography, and their ecological characteristics, and dinosaur survival varied accordingly. This geographic variation in extinction intensity provides important clues about what factors determine survival and why some lineages persisted longer than others. North America, located relatively close to Chicxulub and directly in the path of the impact's most severe, immediate effects, was devastated quickly and thoroughly. The Hell Creek Formation in Montana and the Dakotas, one of the best-studied dinosaur fossil sites in the world, shows a sharp boundary between the Cretaceous and Paleogene periods. Below the boundary, dinosaur fossils are abundant and diverse, representing a thriving ecosystem. Above it, they vanish almost completely, with the transition occurring over a layer just a few centimetres thick. This stark transition suggests that North American dinosaurs were wiped out quickly, likely within decades of the impact, with little opportunity for adaptation or migration to more favourable environments. South America, more distant from the impact site and separated by ocean and geography, may have offered better survival prospects for a time. The fossil record from this region is less complete than North America's due to fewer exposed rock formations from this period and less intensive paleontological exploration, but some evidence suggests that dinosaurs persisted longer here than in North America. The geographic isolation of South America during the late Cretaceous, it was an island continent separated from North America and Africa, meant that its ecosystems were somewhat buffered from global catastrophes and had evolved unique species found nowhere else. However, the impact of winter and subsequent climate disruptions would have reached South America eventually, carried by atmospheric circulation and ocean currents, and the outcome was ultimately the same. Asia presents an interesting and complex case. The continent's vast size and diverse habitats, ranging from coastal plains to high mountains, from dense forests to arid interior deserts, could have provided multiple refugees for dinosaurs seeking to escape the worst effects of the catastrophe. Some paleontologists speculate that small populations might have survived in remote mountain valleys, protected by surrounding peaks, or on islands in the ancient Tethys Sea that separated Asia from Africa and Europe. However, the fossil record doesn't support long-term survival beyond what's seen elsewhere. Asian dinosaur fossils show the same pattern as other continents: abundance and diversity in the late Cretaceous, sudden disappearance at the KPG boundary. If isolated populations did survive longer, they left no trace we've yet discovered. Antarctica and Australia, located in polar regions during the late Cretaceous and connected as part of the southern supercontinent Gondwana, had dinosaur populations already adapted to cold, dark winters. These species, including small theropods and hypsilophodonts that had evolved to cope with months of darkness each year, might have had a slight advantage in surviving the impact of winter. Their physiology and behaviour were already suited to low-light conditions and cold temperatures, giving them a head start compared to tropical species. However, the collapse of plant life would have affected them just as severely as their tropical cousins, eliminating their food sources regardless of their cold tolerance. There's no evidence they survived into the Paleogene, and the unique polar ecosystems they inhabited vanished along with them. Europe, fragmented into an archipelago of islands during the late Cretaceous rather than the unified continent we know today, presents a puzzling picture. The fossil record here is patchy, complicated by subsequent geological activity and sea level changes that have obscured or destroyed many deposits from this critical period. Some islands may have served as temporary refuges, their isolation protecting populations from some of the immediate effects of the impact. Island ecosystems often respond differently to catastrophes than continental ones, sometimes buffering populations against extinction through geographic isolation. However, islands also pose their own challenges: limited resources, small population sizes, and vulnerability to environmental changes. Any dinosaurs that survived on European islands would have faced these constraints, and ultimately, the evidence suggests they succumbed within the same general time frame as their continental relatives. Africa, despite its size and ecological diversity during the Cretaceous, has yielded relatively few fossils from the critical period around the KPG boundary. This isn't necessarily because dinosaurs didn't live there. They certainly did, and African late Cretaceous deposits show evidence of diverse dinosaur faunas, but because the right geological conditions for fossilization and subsequent exposure are rare. The lack of data makes it difficult to assess how African dinosaurs fared, whether they experienced the same rapid extinction seen in North America or a more gradual decline. Until more fossils are discovered and studied, Africa remains a blank spot in our understanding of the extinction's geographic pattern. What these regional variations tell us is that while the asteroid impact was a global catastrophe, its effects played out differently in different places. Distance from the impact site mattered, but so did local geography, climate, and ecology. Some regions may have provided temporary havens where dinosaurs survived weeks or months longer than elsewhere. But temporary is the key word. Eventually, the global nature of the catastrophe caught up with every population. The impact of winter affected the entire planet. The collapse of photosynthesis was worldwide. No region was truly safe, no refuge permanent. The extinction was inevitable, though its precise timing varied by location. The birds, dinosaurs that made it. While non-avian dinosaurs perished across the globe, their descendants, birds, survived and thrived, carrying the dinosaur lineage forward into the Cenozoic era and beyond. This survival wasn't accidental or lucky. Birds possessed several key advantages that allowed them to weather the extinction event when their larger relatives could not. Understanding why birds survived while other dinosaurs didn't provides crucial insights into the nature of the KPG extinction and what factors determine survival in Earth's most famous mass extinction event. Size was a critical factor that determined survival across multiple groups. Most birds that survived the extinction were small, with body masses typically under 1 kilogram. Small animals have lower absolute food requirements than large ones. A sparrow-sized bird needs only a few grams of food per day, while a tyrannosaurus needs hundreds of kilograms per week. In a world where food had become scarce, this size advantage was enormous. Small birds could survive on food sources that wouldn't sustain larger animals, and they could go longer between meals by entering torpor, a state of reduced metabolic activity similar to hibernation. Large, predatory birds like gargantuaves, which stood over a metre tall and likely preyed on other animals, went extinct, along with their non-avian relatives, while smaller seed eaters and insectivores persisted. Diet was equally important in determining which lineages survived. Recent research analysing the fossil record and examining the types of birds that made it through the extinction has shown that the survivors were predominantly seed eaters. Seeds, being durable and long-lived, survived the impact of winter in large numbers, lying dormant in the soil until conditions improved. As plants died during the months of darkness, they released their seeds into the environment as a final reproductive effort, creating a seed bank that could sustain populations for months or years after the parent plants had perished. Birds adapted to eating seeds had a ready food source that persisted when other foods disappeared. Meanwhile, birds dependent on fruit, which requires living plants, or nectar, which requires flowering plants or live prey, which requires functioning ecosystems, struggled and often failed to survive. Mobility gave birds another crucial advantage over ground-dwelling dinosaurs. Unlike their earthbound relatives, birds could fly, allowing them to search for food and water over large areas spanning hundreds of kilometers. If conditions became unbearable in one region, if food ran out or water sources dried up, they could migrate to another region where conditions might be marginally better. This mobility was crucial in a rapidly changing world where favourable conditions were temporary and localised, shifting as weather patterns and local resources changed. A triceratops trapped in a dying ecosystem had no escape, but a bird could take wing and search for better circumstances, increasing its odds of finding the resources needed to survive. The ability to burrow or seek shelter in protected microhabitats also helped many bird species survive the initial catastrophe. Some early birds, like the ancestors of modern waterfowl, were semi-aquatic and could retreat into water or mud to escape temperature extremes during the thermal pulse. Others nested in burrows or hollow trees, providing protection from the searing heat and later from the bitter cold. These behaviours, inherited from their theropod ancestors, which had evolved diverse nesting strategies, proved life-saving during the chaotic hours and days following the impact, when exposed animals perished in massive numbers. Finally, rapid reproduction gave birds a demographic advantage that large dinosaurs couldn't match. Most birds mature quickly, reaching reproductive age within their first year of life, and produce multiple offspring per year through multiple clutches of eggs. This allowed populations to bounce back rapidly once conditions improved, even if mortality had been severe during the worst of the crisis. In contrast, large dinosaurs like tyrannosaurs or hadrosaurs had long maturation times, taking years or even decades to reach breeding age, and produced relatively few offspring. Even if some individuals survived the initial catastrophe, their slow reproductive rates would have made population recovery difficult or impossible in a world where conditions remained harsh and unpredictable. The birds that emerged from the extinction were different from those that went into it. Many Cretaceous bird lineages went extinct, particularly larger forms and those with specialised diets. But the survivors radiated rapidly into the ecological void left by the extinction, diversifying into the tens of thousands of species we see today. They conquered every continent, mastered every habitat, from deserts to rainforests to polar regions, and evolved into forms ranging from hummingbirds to ostriches. The age of birds had begun, and in a very real sense, the dinosaurs never went extinct at all. They simply got smaller, grew more sophisticated feathers, and learned to fly better than they ever had before. The ocean's slow death. While terrestrial ecosystems suffered immediate and dramatic collapse that was visible in the fossil record within years, the oceans experienced a slower, more insidious decline that unfolded over months and years. The asteroid impact had triggered massive tsunamis that radiated outward from the impact site, some reaching heights of hundreds of meters as they scoured coastlines and reshaped shallow seas. These waves traveled across entire ocean basins, reaching distant shores within hours and devastating coastal ecosystems worldwide. But the real killer in the oceans wasn't the immediate physical destruction. It was chemical changes that fundamentally altered ocean chemistry and destroyed the base of the marine food web. When the asteroid vaporized carbonate rocks at the impact site in the Yucatán Peninsula, it released massive amounts of carbon dioxide into the atmosphere. Estimates suggest trillions of tons were released in an instant. This CO2 didn't just warm the atmosphere through the greenhouse effect. Much of it dissolved into the oceans over the following weeks and months, lowering the pH and making the water more acidic. Marine organisms that built shells or skeletons from calcium carbonate, including plankton, ammonites, and many mollusks, found it increasingly difficult to maintain their structures as the ocean chemistry changed. Their shells thinned, weakened, and eventually dissolved as the acidic water literally ate away at them, leaving the organisms vulnerable and unable to survive. The collapse of plankton populations was the first domino to fall in a cascade that would empty the seas. Plankton formed the base of the marine food web, microscopic organisms that convert sunlight and nutrients into biomass through photosynthesis, feeding everything from small fish to filter-feeding giants. When plankton died en masse, both from acidification and from the impact of winter that cut off their light source, the entire ocean ecosystem began to unravel from the bottom up. Fish populations crashed within weeks or months, depriving marine reptiles of their primary food source and creating a starvation crisis that rippled up through every level of the marine food chain. Mosasaurs, the dominant marine predators of the late Cretaceous and rulers of the ancient seas, starved in a world suddenly devoid of prey. These were massive, active hunters, some species exceeding 15 meters in length, that required enormous amounts of food to fuel their muscular bodies and maintain their body heat. With fish populations collapsing and squid becoming scarce, they had nothing to eat. Fossil evidence shows that mosasaurs survived for at least several months after the impact. Their remains found in deposits dating to shortly after the KPG boundary, but eventually they succumbed to starvation. Some specimens show signs of malnutrition in their final days. Thinned bones that suggest calcium deficiency, evidence of metabolic stress in bone structure, and reduced growth rates that indicate inadequate nutrition in the months before death. Plesiosaurs suffered a similar fate through the same mechanisms. These long-necked reptiles with their distinctive body plan, small heads on elongated necks, barrel-shaped bodies, and 4 paddle-like flippers, fed primarily on fish and squid, both of which became scarce as ocean ecosystems collapsed. Their large bodies and active lifestyles required constant feeding to maintain, with estimates suggesting large plesiosaurs needed to consume significant portions of their body weight weekly. The post-impact oceans couldn't support them, and like the mosasaurs, they disappeared within the first year, their distinctive body plan vanishing forever from Earth's oceans. Sea turtles and crocodilians fared better through a combination of physiological and behavioral adaptations. Both groups are generalists, capable of eating a wide variety of foods from fish to vegetation to carrion, giving them flexibility when preferred prey became scarce. Sea turtles can survive for months without eating, drawing on substantial fat reserves stored in their bodies and reducing their metabolic rate to conserve energy. Crocodilians are ambush predators that can go long periods between meals, sometimes months in modern species, and they can survive on surprisingly little food when necessary. These traits allowed them to endure the marine ecosystem collapse, weathering the crisis by reducing activity and living off reserves. Both groups survived into the Paleogene and persist to this day, testimony to the survival value of dietary flexibility and physiological resilience. The recovery of ocean ecosystems took hundreds of thousands of years, far longer than terrestrial recovery, because the damage was chemical as much as biological. Without plankton, the nutrient cycle that sustains ocean productivity was broken. Dead organisms sank to the ocean floor, taking their nutrients with them and removing them from the surface waters where life concentrates. The slow weathering of rocks on land gradually released nutrients that washed into the seas through river runoff. But this was a geological process operating on geological timescales, not a biological one that could respond quickly. It wasn't until the Paleocene epoch, millions of years later, that ocean productivity returned to pre-impact levels and marine ecosystems fully recovered their complexity and diversity. The volcanic connection. While the asteroid impact is rightly considered the primary culprit in the dinosaur extinction, it wasn't acting alone in destroying Mesozoic ecosystems. During the same period, massive volcanic eruptions were occurring in what is now India, a region known to geologists as the Deccan Traps. These eruptions released enormous quantities of lava that eventually covered an area larger than modern India, creating flood basalts thousands of meters thick in places. More importantly for extinction, they pumped greenhouse gases and toxic compounds into the atmosphere on a scale that rivals or exceeds modern industrial emissions, fundamentally altering global climate and atmospheric chemistry. The timing of the Deccan Traps eruptions is controversial and has been intensely debated in the scientific literature. Some evidence suggests the eruptions began hundreds of thousands of years before the asteroid impact and continued for hundreds of thousands of years afterward, making them a prolonged stressor on global ecosystems. If true, this means dinosaurs were already under stress from volcanic activity when the asteroid delivered the final blow. Other evidence suggests the impact itself may have intensified volcanic activity, perhaps by triggering earthquakes that destabilize magma chambers or by sending seismic waves through the Earth that affected volcanic systems worldwide. The combination of volcanic gases, climate instability, and the sudden asteroid impact would have created a 1-2-3 punch that even healthy, robust ecosystems couldn't withstand. Volcanic eruptions release a complex cocktail of gases that affect climate in complex and sometimes contradictory ways. Sulfur dioxide forms aerosols in the stratosphere that reflect sunlight back into space, causing short-term cooling that can last for years after major eruptions. Carbon dioxide, on the other hand, traps heat in the atmosphere through the greenhouse effect, causing long-term warming that persists for thousands or even millions of years. The interplay between these opposing effects would have created wild climate swings, with temperatures seesawing between extremes on timescales of years to decades, making it difficult for organisms to adapt through either physiological or behavioral changes. Plants couldn't adjust their ranges fast enough to track the changing climate, and animals couldn't migrate quickly enough to stay in their preferred temperature ranges. For dinosaurs attempting to recover from the asteroid impact, renewed or ongoing volcanic activity would have been devastating, preventing any meaningful recovery. Just as temperatures began to stabilize after the impact of winter and plant life started to cautiously recover, volcanic eruptions would have disrupted the process, releasing new pulses of sulfur dioxide that created additional cooling episodes or pumping out carbon dioxide that caused rapid warming. The climate seesawed between freezing and scorching, preventing ecosystems from finding equilibrium and making it impossible for populations to rebuild. Each time conditions improved marginally and survival seemed possible, a new volcanic pulse would reset the process, creating a treadmill of extinction that ground down surviving populations. Some paleontologists have argued that the Deccan Traps, not the asteroid, were the primary cause of the extinction, pointing to evidence that they would cite as showing dinosaur diversity was already declining in the millions of years before the impact. They note that volcanic eruptions can cause many of the same effects as asteroid impacts: climate change, atmospheric darkening, acid rain, ocean acidification, but spread over longer timescales. However, most scientists now believe the asteroid was the decisive factor, the coup de grace that finished what volcanism had started. The impact caused immediate, catastrophic effects that volcanism couldn't match, and the timing is too perfect to be coincidental. The extinctions align with the impact, not with any particular phase of Deccan volcanism. The truth probably lies somewhere in between these extremes. Volcanism may have weakened ecosystems and reduced biodiversity before the impact, making them more vulnerable to catastrophe. Then the asteroid delivered a blow that healthy ecosystems might have weathered, but stressed ones could not. Finally, continued volcanism after the impact prevented recovery, ensuring that the extinction was total rather than partial. It was a perfect storm of catastrophes, each amplifying the others, that sealed the fate of the non-avian dinosaurs and ended the Mesozoic era forever. The fossil record's gaps and limitations. Understanding what happened to dinosaurs after the asteroid impact is challenging because the fossil record is incomplete, biased, and difficult to interpret. Fossils form under specific conditions: rapid burial, low oxygen environments, mineral-rich sediments. And these conditions aren't evenly distributed across the planet or through time. As a result, we have excellent records from some regions and time periods, detailed windows into ancient worlds, and almost nothing from others, leaving frustrating gaps in our knowledge. This unevenness creates challenges for paleontologists trying to reconstruct the precise timeline and geographic pattern of the extinction. The Hell Creek Formation in Montana, North Dakota, and South Dakota provides a detailed snapshot of the final days of the Cretaceous period in North America. Fossils are abundant, well preserved, and span the critical period before and after the impact, allowing paleontologists to track changes in dinosaur populations with remarkable precision. The formation includes hundreds of dinosaur specimens representing dozens of species, from massive triceratops to small bird-like theropods. This allows scientists to document the composition of late Cretaceous ecosystems and see how they changed across the KPG boundary. But Hell Creek isn't representative of the entire planet or even all of North America. What happened in Asia, South America, or Africa might have been different, and we have fewer fossils from those regions to tell us the story. Another issue complicating interpretation is the Signor Lips effect, a statistical artifact named after the paleontologists who first described it. This effect makes extinctions appear more gradual in the fossil record than they actually were in reality. Here's why. Rare species are less likely to fossilize than common ones, simply because there are fewer individuals to potentially become fossils. Therefore, their last appearance in the fossil record often predates their actual extinction by a significant margin, potentially thousands or even millions of years. This creates the illusion of a slow decline, when the reality might have been a sudden collapse. For dinosaurs, this means we might be missing evidence of species that survived longer than the fossil record suggests. Or conversely, species might appear to disappear before the boundary when they actually survived until the impact itself. Temporal resolution presents another significant limitation on our understanding. The KPG boundary represents a geological instant, but that instant could span thousands of years when we account for the limitations of dating techniques and the time it takes to deposit sediments. When we say a dinosaur went extinct at the boundary, we mean it disappeared sometime during that window, which might represent 10,000 years or more. Whether it died the day after the impact, a year later, or 10,000 years later is often impossible to determine with current methods. This temporal smearing makes it difficult to construct precise timelines of extinction and recovery. Geographic coverage is also highly uneven, creating blind spots in our understanding. Some regions have been intensively studied by paleontologists for over a century, with thousands of specimens collected and analysed. Others remain virtually unexplored, either because they lack exposed rocks of the right age, or because political, economic, or logistical factors have prevented research. Large parts of Africa, Asia, and South America have fossil deposits that likely contain crucial evidence about the extinction, but they remain unstudied or understudied. Until we have better global coverage, our understanding of the extinction's geographic pattern will remain incomplete. Despite these significant limitations, the fossil record tells a clear and consistent story across multiple sites and continents. Below the KPG boundary, dinosaurs are abundant and diverse, representing thriving ecosystems with complex food webs. Above it, they're gone, vanished with a thoroughness that's stark and unmistakable. The transition is sharp, especially in well-studied sites like Hell Creek, where the change occurs over a layer just centimetres thick. While some species might have lingered longer than others in isolated refuges, and while the precise details of timing and geography remain uncertain, the overall pattern is unmistakable. The asteroid impact triggered a mass extinction that wiped out the non-avian dinosaurs and ended their reign as Earth's dominant land animals. The mammals inherit the Earth. In the ecological vacuum left by the dinosaurs' extinction, mammals exploded in diversity and size with remarkable speed, transforming from minor players to dominant fauna within a few million years. For 160 million years throughout the entire Mesozoic era, mammals had lived in the shadows of dinosaurs, kept small and primarily nocturnal by the dominance of their reptilian contemporaries. Most Mesozoic mammals were no larger than rats or small cats, filling ecological niches that didn't bring them into direct competition with dinosaurs, eating insects, seeds, or other small prey that dinosaurs largely ignored. The extinction removed that constraint suddenly and completely, and mammals seized the opportunity with an evolutionary explosion unmatched in their history. Within a few 100,000 years of the impact, new mammal species appeared in the fossil record, their bones showing up in Paleocene deposits across the world. They were still small by modern standards. Most were no larger than a house cat, and many were significantly smaller. But they were diversifying rapidly, splitting into new lineages that explored different ecological roles. They evolved new diets, from strict herbivory to carnivory to omnivory. They developed new locomotion styles, from ground dwelling to climbing to gliding. They occupied new habitats, from forests to grasslands to wetlands. The pace of change was dizzying compared to the slow, steady evolution of the Mesozoic. By 10 million years after the extinction, mammals had radiated into dozens of distinct lineages that would eventually give rise to all modern mammal groups. Early primates appeared, small tree-dwelling insectivores that were nothing like modern apes, but were our distant ancestors nonetheless. The ancestors of modern hoofed mammals evolved, though they looked nothing like horses or deer. They were small, generalized animals with simple teeth and unspecialized feet. Early carnivores emerged, though they weren't yet the specialized predators we see today. Rodent ancestors appeared, destined to become the most diverse and successful mammal group. This radiation filled the fossil record with new forms appearing at a pace that seems almost frantic. Body sizes increased dramatically as mammals evolved to fill the large-bodied niches left empty by dinosaurs' extinction. Where the largest Mesozoic mammals weighed just a few kilograms, about the size of a modern badger, Paleocene mammals grew to tens or even hundreds of kilograms within a few million years. By the Eocene epoch, just 15 million years after the extinction, mammals had evolved that weighed over a ton. This size increase happened independently in multiple lineages as different groups discovered the advantages of large body size, better defense against predators, ability to process low-quality plant food, thermal regulation in changing climates. This rapid diversification wasn't random or directionless. Mammals were filling the ecological niches left vacant by dinosaurs, evolving to perform the same ecological functions that dinosaurs had performed for over 160 million years. Large herbivores evolved to browse vegetation and graze on plants, replacing hadrosaurs and sauropods as the primary consumers of plant matter. Medium-sized predators took over the roles once held by tyrannosaurs and dromaeosaurs, becoming the top predators in post-extinction ecosystems. Even the skies saw new mammalian entrants, with bats evolving powered flight within 15 million years of the extinction, filling niches once occupied by pterosaurs. The success of mammals was partly due to traits they had evolved during their long subordination in the Mesozoic, adaptations that had allowed them to survive in the shadows, but now gave them advantages in the Paleocene world. Their warm-blooded metabolism, more sophisticated than the mesothermy of dinosaurs, allowed them to remain active in the cooler post-impact world and to colonize a wider range of climates. Their diverse dentition, incisors for cutting, canines for gripping, premolars and molars for grinding, enabled them to process a wide variety of foods, from tough plant matter to meat to insects. And their reproductive strategies, including live birth and extended parental care that allowed mothers to nurture young through their most vulnerable period, gave their offspring better survival odds than dinosaur hatchlings that had to fend for themselves. But mammals didn't just replace dinosaurs in a simple one-to-one substitution. They transformed ecosystems in ways dinosaurs never had, creating new ecological relationships and patterns. They developed new symbiotic relationships with plants, dispersing seeds through their digestive systems and pollinating flowers with their fur. They engineered landscapes more actively than dinosaurs had, digging extensive burrow systems that altered soil structure and creating dens that other animals could use. And they evolved intelligence and social complexity that eventually exceeded anything seen in the Mesozoic, with some lineages developing remarkably sophisticated behaviours and communication systems. Climate recovery and stabilisation. The climate chaos triggered by the asteroid impact didn't resolve quickly or smoothly. For thousands of years, Earth's climate systems remained unstable, swinging between extremes as competing feedbacks battled for dominance and atmospheric composition changed. Eventually, however, the climate began to stabilize through a series of gradual adjustments, setting the stage for ecosystem recovery and the emergence of the Paleocene world. This stabilization was a complex process involving the atmosphere, oceans, and biosphere, each influencing the others in intricate ways. The first step toward recovery was the clearing of the atmosphere from the dust and aerosols that had blocked sunlight and triggered the impact of winter. The dust and aerosols that had been thrown into the stratosphere by the impact gradually settled out of the upper atmosphere, falling to the ground under gravity's inexorable pull or being washed out by precipitation. Within a few years, enough sunlight penetrated the atmosphere to allow photosynthesis to resume at meaningful levels, though it would take much longer for full sunlight to return. Plants began to grow again, slowly at first as conditions remained marginal, then with increasing vigour as light levels improved and temperatures stabilised. Carbon dioxide levels, elevated dramatically by both the impact and the ongoing Deccan Traps volcanism, remained high for hundreds of thousands of years after the extinction. This created a greenhouse effect that warmed the planet, partially offsetting the cooling from the impact winter and eventually pushing temperatures above pre-impact levels. The warming was uneven, affecting different regions differently and creating new climate patterns. Polar regions warmed more than tropical ones, reducing the temperature gradient between equator and poles. Precipitation patterns shifted as atmospheric circulation changed in response to the new temperature distribution. These regional climate differences shaped the recovery, determining which areas could support life first and which remained barren longer. Ocean circulation patterns, disrupted profoundly by the impact and subsequent climate changes, took even longer to recover than atmospheric conditions. The thermohaline circulation, the system of currents driven by differences in water temperature and salinity that distributes heat around the planet, had been thrown into chaos by the injection of cold fresh water from melting ice, changes in surface temperature, and altered evaporation patterns. Cold, fresh water from glacial melting mixed with warm, salty seawater, creating density gradients that stalled normal circulation patterns. It took tens of thousands of years for normal patterns to re-establish as the ocean's temperature and salinity structure gradually returned to equilibrium. As the climate stabilized, ecosystems began to rebuild from their shattered state. The process was slow and uneven, proceeding at different rates in different regions depending on local conditions. Tropical areas, with their higher baseline productivity and warmer temperatures that supported faster plant growth, bounced back faster than polar regions, where cold temperatures limited biological activity. Coastal zones, fed by nutrient-rich runoff from eroding highlands, recovered before inland areas that lacked this nutrient subsidy. Lowland areas with deep soils recovered faster than highlands where thin soils limited plant growth. The new ecosystems that emerged didn't resemble those of the Cretaceous in composition or structure. The species compositions were fundamentally different, with new dominant groups replacing those that had gone extinct. The ecological dynamics had shifted, with different predator-prey relationships and different competitive hierarchies. Flowering plants, which had been relatively minor players in many Mesozoic ecosystems, became dominant in the Paleocene, covering vast areas and forming the base of no food webs. Mammals replaced dinosaurs as the primary large-bodied fauna, evolving to fill the roles that dinosaurs had occupied. Insects co-evolved with the new flowering plant species, creating novel pollination systems and developing new feeding strategies. Within 1 million years of the impact, the planet had largely stabilized climatically. The Paleocene epoch had officially begun, marked by new ecosystems, new dominant groups, and new ecological patterns. While scars from the extinction remain visible in the fossil record, the missing species, the simplified ecosystems, the reduced diversity, life had adapted and moved forward with characteristic resilience. The age of dinosaurs was over, ended by catastrophe. The age of mammals had begun, built on the ruins of what came before. Lessons from the extinction. The KPG extinction holds lessons that resonate powerfully today as we face our own environmental crisis. It demonstrates how interconnected ecosystems are, revealing that the collapse of one component can trigger cascading failures throughout the entire system in ways that are difficult to predict or prevent. It shows that even the most successful, dominant groups, species that had thrived for millions of years and seemed perfectly adapted to their world, can be vulnerable to sudden environmental change they're not equipped to handle. And it reveals that extinction isn't always instant or simple. Sometimes it's a drawn-out process that unfolds over generations through multiple mechanisms, making survival depend on a complex combination of traits and circumstances. For dinosaurs, the extinction was multifaceted and complex, not a simple story of an asteroid killing everything instantly. The asteroid impact was the trigger, the initiating event that set everything in motion. But the actual dying involved starvation as food chains collapsed, disease as stressed populations became vulnerable to pathogens, climate stress as temperatures swung wildly, reproductive failure as nesting became impossible, and ecosystem collapse as the intricate web of ecological relationships unraveled. No single factor killed all the dinosaurs. It was the combination, the perfect storm of multiple stresses acting together, that proved lethal. This complexity is important for understanding modern extinction events, which also typically involve multiple interacting stresses rather than single causes. The extinction also highlights the crucial role of chance in determining survival. Birds survived while non-avian dinosaurs didn't, not because they were objectively better in any absolute sense, but because they happened to have traits, small size, seed-eating diet, mobility, rapid reproduction, that were advantageous in that specific catastrophe at that specific time. In a different extinction event, with different characteristics, the survivors might have been entirely different. A catastrophe that killed seed eaters but spared large animals would have produced a completely different outcome. Evolution doesn't prepare organisms for every possible disaster because it can't predict the future. It can only work with variation that already exists in populations, adapting organisms to current conditions without regard for what might happen tomorrow. Finally, the extinction shows that recovery is possible but agonizingly slow when measured on human timescales. It took millions of years for ecosystems to fully recover from the KPG extinction, to rebuild the complexity and diversity that had been lost. Biodiversity did rebound eventually, new species evolved to fill empty niches, and life found a way forward as it always has through Earth's long history. But the world that emerged was fundamentally different from the one that existed before. The dinosaurs were gone forever, replaced by mammals that evolved into forms the Mesozoic never saw. The Mesozoic had ended completely, and a new era with new rules and new dominant groups had begun. For us, living in a time of rapid environmental change driven by human activity, these lessons from deep time are sobering and relevant. The KPG extinction reminds us that ecosystems can collapse when pushed past critical thresholds, that dominant species can disappear despite millions of years of success, and that recovery, while inevitable on geological timescales of millions of years, is far too slow to matter for species caught in the crisis or for human societies dependent on functioning ecosystems. The dinosaurs didn't go extinct immediately when the asteroid hit, but they went extinct nonetheless, ground down by cascading failures over years and decades. And once they were gone, vanished from every continent and ocean, they never came back. The Mesozoic ended not with a bang, but with a whimper, as the last surviving dinosaurs died alone in a world that had moved on without them. The last dinosaurs, final days of an ancient lineage. Somewhere in the ruins of the Cretaceous world, perhaps in a sheltered valley protected by mountains, or on a remote island buffered from the worst of the climate chaos, the very last non-avian dinosaur took its final breath. We'll never know what species it was, where exactly it lived, or when precisely it died. The fossil record can't capture individual deaths or pinpoint the exact moment a lineage ends. But we know with certainty that this moment came. There was a last dinosaur, a final representative of a dynasty that had ruled Earth for 160 million years. And when it died, an entire age died with it. Understanding what those final days might have been like, based on our knowledge of the extinction and its effects, provides a poignant end to the dinosaur story. The last surviving dinosaurs would have been living in a world utterly transformed from the one their ancestors had known. Gone were the lush forests filled with flowering plants and buzzing insects, the wide plains where herds migrated seasonally, the complex ecosystems with their intricate food webs and predator-prey relationships refined over millions of years. In their place was a grey, diminished landscape, sparse vegetation struggling to recover, simplified ecosystems with only a fraction of their former diversity, a world fundamentally broken and trying haltingly to rebuild. These final dinosaurs were survivors of multiple catastrophes, individuals or small populations that had weathered the thermal pulse, survived the impact of winter, endured the starvation years, and persisted through the climate chaos that followed. They would have been nothing like their pre-impact ancestors in behaviour or lifestyle. Natural selection operating under extreme pressure favours dramatic changes, and any dinosaurs that survived years or decades into the post-impact world would have been fundamentally altered by their experience. They would have been scavengers rather than specialised predators or grazers, eating whatever they could find regardless of their ancestral diet. They would have been opportunistic and flexible, abandoning the specialised behaviours and ecological niches that had defined their species. They would have been desperate, driven by hunger and the constant struggle to find enough food and water to survive another day in a hostile world. size would have shifted downward through the brutal process of selection. Large animals, with their enormous food requirements and long maturation times, would have been among the first to disappear as ecosystems collapsed. The survivors would have been smaller species or individuals, those that could subsist on minimal resources and reproduce relatively quickly. Perhaps they were the size of chickens or turkeys, small enough to survive on insects and seeds, mobile enough to search for scarce resources across wide areas. Their bones would have shown signs of malnutrition, thinned cortices, reduced density, evidence of arrested growth during the worst periods. They would have been shadows of what their species had been in the Cretaceous, diminished in every way. Social structures would have broken down completely as populations fragmented and scattered. Dinosaurs had been social animals, many species living in herds or family groups, communicating through calls and visual displays, cooperating in raising young or defending territory. But social behaviour requires population density and stable environments. With populations reduced to handfuls of individuals scattered across vast territories, with resources too scarce to support groups, with environmental conditions changing too rapidly for traditional behaviours to function, these social bonds would have dissolved. The last dinosaurs likely lived solitary existences, rarely if ever encountering others of their species, their complex social behaviours forgotten or impossible to express. Reproduction would have become increasingly difficult or impossible, sealing the fate of even those individuals that survived. Dinosaurs laid eggs that required specific conditions, appropriate temperatures for incubation, safe nesting sites protected from predators and weather, sufficient food for the mother during egg production, and for hatchlings after emergence. The post-impact world provided none of these requirements reliably. Ground temperatures fluctuated wildly as the climate remained unstable. Safe nesting sites were buried under ash or destroyed by erosion. Food was too scarce for mothers to produce viable eggs or for hatchlings to survive their vulnerable first months. Without successful reproduction, populations couldn't replace individuals lost to predation, disease, or old age, creating a demographic death spiral that made extinction inevitable, regardless of how well adapted the survivors were. The psychological experience of these final dinosaurs is impossible to know, but worth contemplating. Were they aware that they were the last, that their kind was ending? Almost certainly not. Animals don't think in those terms, don't conceptualize extinction or the end of lineages. But they would have experienced the loneliness of their situation, the absence of the social bonds their species had evolved to depend on. They would have felt hunger as a constant companion, the gnawing emptiness that came from never finding quite enough food. They would have known fear as their world grew strange and hostile, as familiar patterns disappeared and nothing made sense anymore. Perhaps the very last dinosaur was an old individual, one that had survived through luck and resilience longer than any of its contemporaries. Perhaps it had memories, if dinosaurs had such things, of a time before the impact when life was easier and food was abundant. Perhaps it searched for others of its kind, calling out with vocalizations that went unanswered, wandering through empty territories where its species had once thrived. Or perhaps it was young, born in the post-impact world, knowing nothing of what had been lost, simply trying to survive in the only world it had ever known. When that last dinosaur died, whether from starvation, disease, predation, or simply old age, there was no one to witness it, no marker to commemorate the end of an era. Its body likely decomposed without fossilizing, consumed by scavengers, or broken down by bacteria, returning its atoms to the soil. The location became just another patch of ground, indistinguishable from any other, with nothing to indicate that here the Mesozoic had truly ended. But the significance of that moment echoes through time nonetheless. The non-avian dinosaurs were gone, their incredible evolutionary radiation terminated, their ecological dominance ended. Earth belongs to new forms now, to mammals rising to fill empty niches, to birds carrying the dinosaur legacy forward in new forms, to ecosystems rebuilding themselves according to new patterns and rules. The last dinosaur's death was both an ending and a beginning. It closed a chapter in Earth's history that had lasted for 160 million years, longer than mammals have yet reigned. But it opened the door to new possibilities, new evolutionary experiments, new forms of life that would never have emerged if dinosaurs had continued their dominance. In the grand scope of evolutionary time, extinctions create opportunities as much as they destroy diversity. The end of the dinosaurs allowed the rise of mammals, which eventually gave rise to primates, which eventually gave rise to humans capable of uncovering this story and contemplating its meaning. The last dinosaur's death was tragic for its lineage, but transformative for Earth's future. A reminder that endings and beginnings are often the same moment seen from different perspectives.